Let's get started on chapter 6 on normal probability distribution. So normal probability distribution is probability distribution. So it follows two requirements. First one is total probability, sum of the p of x equal to 1. Second condition is each individual probability is greater equal to 0, less equal to 1. That's requirements for all the probability distribution. And normal probability distribution is a special probability distribution. In this chapter, we'll focus on continuous random variable. Chapter 5, we focus on the discrete random variable. So on chapter 6, we focus on continuous random variable. So normal probability distribution actually describe the characteristics of the continuous random variable. And following is a normal distribution in terms of the graphing. Curve is a bell-shaped curve, and the total probability here, summation of p of x equal to 1. So total probability under total area under the bell curve is equal to 1. And also it's a symmetrical curve, symmetrical with respect to the mean. So the mean cut the entire bell curve into half and half. So each one occupies 0.5. And this is the mathematical formula we use to describe the normal probability distribution. And here involved the x represent a continuous random variable. We also have a mean, population mean, population standard deviation. We also have a pi. Pi is approximately equal to 3.1415. Okay. Also the E. E is a natural number, is approximately 2.18. Okay. 2.718. So before we get to the normal probability distribution, let's start with the standard normal distribution. Again, this is standard normal distribution is a special normal distribution. And the special thing about the standard normal distribution is graph is still bell-shaped curve. Okay, we still use a bell curve to represent a standard normal distribution. And then the mean is equal to 0, mu equal to 0, standard deviation equal to 1. So if you're using z-score formula, x minus mu equal to over sigma, when mean equal to 0, x minus 0, sigma equal to 1, simplify you get x. So the z-score, standard normal distribution, the z-score is the same as the discrete random variable x. Okay, so that's a very special feature of the standard normal distribution. And in this particular section, we're going to develop a skill to find areas. We call that probability. Area probability, that means the same thing. We're going to use z-score as a tool to find the corresponding area under the graph. So the continuous random variable has a uniform distribution if its values are spread evenly. Okay, that uniform distribution basically represented using the rectangular. So right here, this is starting point A, ending point B. Uniform probability distribution is also another type of a probability distribution. That means total area for this rectangle, total area for a rectangle is equal to 1. That means same thing from summation of P of x equal to 1. Total probability and the curve in this rectangular shape is equal to 1. So if you know the base, so let's say starting point is A, ending point is B, so here this is B minus A. So the height, since area is equal to 1, so the height is always 1 over B minus A. So in that case, if you multiply the base times height, you always get 1. Base times height, 1. Density curve is same thing as probability at any given point from A to B. So graph continuous probability distribution. The total area under the curve must equal to 1. Every point on the curve must have the same vertical height. Here the vertical height represents probability at that given point, which is always 1 over B minus A. Assuming it's from A to B. Okay. The height is the probability, P of x. One over B minus A. That's the probability for any given point here on the horizontal axis. So because the total area under the density curve is equal to 1, so that's correspondence between the area and then probability. For example, using area to find probability, given the uniform distribution illustrated, find the probability that the randomly selected voltage level is greater than 124.5 volts. So as you can see, this is uniform distribution between 123 volt to 125 volts. That means the base here is equal to 2. It's 125 minus 123. That's equal to 2. Since base is 2, total area equal to 1, height must be half. So this is the height. Height is probability, the half is 0.5. So that's why the height is 0.5. So we're looking at voltage level which is greater than 124.5. So we're looking at this particular rectangle area here between 124.5 to 125.5. 125. So we're still using the base. Now the new base is 125.0 minus 124.5 times the height. Height is the same 0.5. So that becomes 0.5 times 0.5. So that's why the area here is equal to 0.25. Okay, so same thing as calculation presented here. So you have 25% of chance that selected voltage level is greater than 124.5. So the standard normal distribution is the normal probability distribution with mu equal to 0, sigma equal to 1. So another special thing about this is z-score is the same thing as x value because of those two conditions. So again, area equal to 1 and symmetrical with respect to center, z-score equal to 0, right in the middle. Find the probability when given z-score. So give z-score is like a tool we use to find the probability. So typically we're either using technology, meaning you can use Excel, you can use calculator, all the different like statistical software, or the table A2. technology is strongly recommended. Okay. In this course, you can just focus on table A2. If you know how to use technology, that would be great. If you don't, that's fine. Alright, so method for finding normal probability distribution areas. You can use table A2, statistic, Minitab, Excel. Table A2 is the actual table. I'm going to show you where to find that. Statistical software, Minitab is the same thing. Excel, you can also find a probability using Excel. You can use a calculator, TI 83, 84, 89, 92. This is what a table A2 look like. Okay, so table A2, you can use a z-score here. This represents z-score. Z-score we run in 2 decimal places. 2 decimal places. So if let's say z-score is given to be negative 2.48, so now you have 2 digits here, 10th digit, 100th digit. So now 100 digit is 8, right? So this is 100 digit. You locate it on the first horizontal line, and then whole number, and then 10th digit you locate it here. So negative 2.48. So it's split into 2 different digits. Now they have an intercept, and the intercept turned out to be the probability here. So the probability turned out to be 0.00. Turned out to be 0.0066. Sorry. And the table A2 only gives us area to the left, meaning if you draw the bell curve with a z-score equal to negative 2.48, then the area to the left turned out to be, basically on the left tail, turned out to be 0.0066 from the, when you look it up. Okay. And this is only one part of the table. If you go back to the table A2, the actual table A2, right here, as you can see, you have a 2-page, right? You can easily find this on the formula sheet, posted on the blackboard. You just go scroll down to the table A2, and on the table A2 you'll be able to find most of the z-scores here, negative 3.50 and lower using this. And it will give you different decimal places. Also, we have a second page is on a positive z-score, right here. So all these positive z-score, again, it measures area to the left. Okay. And let's continue here. So the table A2 is only for standard normal distribution, mean zero standard deviation. Or another way of saying that is you always need to standardize using a z-score. Okay, to capture the probability. Only 2 pages. One page, first page is for negative z-score, second page is for the positive z-score. And every value in the body of the table is cumulative area from the left up to the vertical boundary above a specific z-score. Again, it says given any z-score, right? The table only gives us area to the left. Table A2 delivers only the area to the left. Okay, I'm working with the graph, confusing between z-score and the areas. So using z-score to find the area, but z-score is not the same as the area. Use the z-score to find the area. So we run the z-score to 2 decimal places, 100th digit. And so then use that to find out the corresponding area. Now let's take a look at the example. Let's say we have a bone mineral density test could be useful in identifying the presence of osteoporosis. The result of this test is commonly measured as a z-score. Has a normal distribution, mean equal to 0, standard deviation equal to 1. So this given condition indicates it's the standard normal distribution. So randomly selected adult undergoes a bone density test. And the probability that the result is reading is less than 1.27. Again, if you're using z-score formula, here this is given the result is x equal to 1.27. You can easily use this to find the z-score, x minus mu over sigma. We know the mean, we know the sigma, we know the x value. So it's 1.27 minus 0 over 1, that turned out to be 1.27. So for the standard normal distribution, again, z-score equal to the continuous random variable, in this case is 1.27. Since z-score equal 1.27, you go to table A2, 1.2, second page of the table A2. Then you can see 1.2 and then 7, intercept becomes 0.8980. So the area here to the all the way to the left on table A2 turned out to be 0.8980. And then we're looking for the area to the left. So the probability here is 0.8980. Okay. If you want to look for the area on the right, it should be total area under the bell curve 1 minus 0.8980. That turned out to be 0.1020. That's the area to the right hand side of that z-score. Okay. So the probability of a random adult having a bone density less than 1.27 is 0.8980. So using the same bone density test, find the probability that the randomly selected person has a result above negative 1.00, which is considered to be the normal range of the bone density. So again, from the table A2, we can see that z-score equal to negative 1.00 give us probability of 0.1587. So this is the area to the left. Now the area to the right, we're looking for the area to the right. For the z-score greater than negative 1.00, that will turn out to be 1 minus 0.1587. This turned out to be 0.8413. So that's why the probability of a randomly selected adult having a bone density above negative 1 is 0.8413. So the keyword here is above. Above indicates we want an area to the right. Below tells us area to the left. Between tells us area in between. Now again, one more time here, bone density reading between negative 1.00 and negative 2.50 indicate subject has osteopenia. Find this probability. So the area to the left of z-score equal to negative 1.00. We use table A to find that. We have the area to the left of negative 2.50 is 0.00862. Since we're looking for the area in between, so using the bigger area here, subtract smaller area. So this smaller area goes here, negative 2.50. Then we get a desired area in between. So this is what we're looking for. So find the difference between those two. This area minus this area, you get 0.1525. And that's probability for the bone density reading between negative 1.00 and then negative 2.50. So always using bigger area, subtract a smaller area to get the area in between. Denotes probability of z-score greater than A, less than B. Denotes probability that z-score is between A and B. So that's area in between. Z-score greater than A, we're looking for the area greater than, that's what we call the area to the right. And then z-score less than A denotes probability that z-score is less than A. So we will look for the area to the left. We also sometimes have to find the z-score from a known area. For example, you draw the bell curve. You find out that you want to find out this z-score given the area to the left. Okay, let's say it's 0.95. So you know the area, you want to go backwards to find the z-score. First of all, you draw a bell-shaped curve, identify a region under the curve that corresponds with the given probability, and use the cumulative area from the left, locate the closest probability in the body of the table A2. So, and then identify corresponding z-score. So for example, if let's say area to the left here turned out to be 0.95, you go back to the table A2, to the second page of table A2, go to center of the table, look for 0.9500. You follow the direction here, you see 0.9500 is right in the middle of 0.9495, 0.9505. So these turn out to be the average of 1.64 and 1.65. And follow the direction arrow here, go down to the bottom, you get z-score equal to 1.645. That's how you find the z-score given the probability. So basically you go to the center of the table and then going backwards to trace down the corresponding z-score. Okay. And let's go back to the PowerPoint. So the z-score here turned out to be 1.645. It's equal to 1.6 plus 1.65, 1.64 plus 1.65 divided by 2, 1.645. Okay. Yeah, that's exactly what we try to do here. Area equal 0.95. Area to the right is 0.05. You basically find the 95th percentile. Or you can say that find the z-score separating the bottom 95% from the top 5%. Find the z-score. You also look at it that way, or you can use percentile, meaning try to locate on the z-score correspond to the 93rd percentile, and the z-score turned out to be 1.645. You go back to the center of table A2, trace back down to the z-score. Yeah. And using the same bone density test and find the bone density score that separates the bottom 2.5%, find a score that separates the top 2.5%. So 2.5%, if you turn into a decimal, it turned out to be 0.025. On the left tail, you get a 0.025. Then go back to table A2, you'll be able to find out the corresponding z-score, which is negative 1.96. And since it's symmetrical, using a symmetrical property, we know that the positive z-score here will be 1.96 on the right. Bell curve is symmetrical. Okay. Well, you can also use the total area accumulated to the left. For the positive z-score, the total area accumulated to the left is going to be 0.95. So 1 minus 0.025 turn out to be 0.975. So use 0.975, locate the positive z-score here, 1.96. For the standard normal distribution, the critical value is a z-score separating unlikely values from those that are likely to occur. The expression z alpha denotes a z-score with an area of alpha to the right. So if you do this, draw the bell curve, z alpha here indicates area to the right equal to alpha. Okay. Let's find the value of the z alpha equal 0.025. So again, draw the bell curve. Now we know the area to the right here equal to 0.025. Now using the complement of this, area to the left will be 1 minus 0.025. That turned out to be 0.975. Now using 0.975, go back to the table A2. Okay, let me show you one more time. Again, open the page, table A2. We look for 0.975, and we should have the exact same match. 0.975 here turned out to be this. Okay, so the corresponding z-score is 1.96. Okay, 1.9 and 6 corresponds with area of 0.9750. Now let's go back here one more time. According to this, area to the left is 0.975, area to the right is 1 minus 0.025. Look at that. Area to the right, 0.025, and the cutoff z-score here on the table is 1.96. Okay. Again, we're using area to find out the z-score, corresponding z-score.